So in the previous lecture, we had seen chaos in the Lorentz equations. We had seen what the strange attractor looks like, and we had made two important comments about the strange attractor. One was that no matter how close to initial conditions are, if two initial conditions are different from each other, after a certain point of time, they separate from each other, and the two trajectories do not look anything like one another. Okay, so the trajectories have very different evolutions, even if they start from points which are very close together. That was one thing which we had mentioned earlier. So that was what was known as sensitive dependence on initial conditions. The second important point that we had mentioned in about the Lorentz attractor is that the attractor's shape. So the shape neither looks like a three-dimensional object because, as you had seen from the volume contraction hypothesis, the volume of the attractor should go to zero. At the same time, the area, it does not look like a two-dimensional object at the same time, because it seems as if there are infinite number of convoluted surfaces in the attractor, and all these convoluted surfaces give an impression of the fact that the area that the attractor is not two-dimensional, but it might be looking like a volume from certain angles. So it seemed that the dimension of the attractor was neither two nor three. So what was it? So we said that the attractor had a fractional dimension, which is also known as a fractal. So the attractor looks like a fractal. So these are the two things that we will be mainly focusing on in this current lecture. So let us look at the first thing. Sensitive dependence on initial conditions. We said that they can be quantified with the help of certain exponents, which are known as these Lyapunov exponents. So the Lyapunov exponents are defined in this manner. So suppose I have two initial positions in space. Okay, so if I denote this one as x dot, and then the second one, I call it x naught plus delta x naught, okay, where the separation between them is delta x naught. And suppose they move around like this in the attractor. So this is one trajectory, and this goes like this, and then it goes like that. So this is one trajectory, and this is this one. So the next question is, suppose at time t, so this is at time t equal to 0, okay, and suppose at time t equal to t, this trajectory comes somewhere over here. We call this location x2 at time t, and this is x1 at time t. So the question that we ask is, what is the new distance between these 2 points? So this is, suppose delta x at time t, which is roughly x2 at t minus x1 at t. Okay, and its magnitude is nothing but the magnitude of the separation vector. So we define these Lyapunov exponents as follows. So the exponent lambda, which is defined as 1 by t log of delta x by the initial separation between the trajectories. So this sign basically means I take the norm of the vector. That means the magnitude of the separation. So this is how I define the Lyapunov exponent. So a few things to note about this is that if there are, so number of Lyapunov exponents in the system is equal to the number of phase space dimensions. So if I have an n-dimensional phase space, then the Lyapunov exponents are lambda 1, lambda 2, all the way up to lambda n. So there are n number of Lyapunov exponents in such a system. Okay. Now, what characterizes a chaotic system? So you see that the when we write the Lyapunov exponent in this form, what we actually calculate is the maximum Lyapunov exponent. Why? The reason is as follows. So suppose you have a volume in phase space. Okay, and the volume is basically classified by the three axes, x, y, and z axis. For the simple case, we consider three-dimensional phase space. After a time t, this volume gets deformed to something like this. Okay, so you see that this can also be decomposed into three orthogonal axes. So there is an expansion along this direction, and there is a contraction along this direction. And similarly, along the other direction, there might be an expansion or the contraction. So since it is a three-dimensional space, then there are only three Lyapunov exponents here. And what happens is that the sum of the Lyapunov exponents, it gives me the rate of expansion or contraction of the volume. Okay. Now, why it does so? It basically follows from the volume contraction hypothesis for the Lorentz equation, which we had seen earlier. Okay, so if you think about the dynamical system to be of this form, then the rate of change of volume or the volume at time t is given by volume at time t equal to 0 into exponential of minus divergence of this vector into time, sorry, plus divergence of the vector into time. So this was what we had seen for this was the expression of how an infinitesimal volume evolves in phase space. All right. Now, if you look at this quantity, gradient of f, gradient of f, I mean, sorry, divergence of f is nothing but equivalent to summation over n lambda n. So this thing is proportional to the sum over the Lyapunov exponents. All right. In fact, this thing is equal to the sum over the Lyapunov exponents. Why that is the case? That can be easily seen from this expression. So you have divergence f given by del fx del x plus del fy del y plus del fz del z. Okay. And you also have the dynamical equations given as x dot equal to fx, y dot equal to fy, and z dot equal to fz. Okay. So now, if I consider a perturbation in the direction of x, okay, suppose I perturb the x vector by x plus delta x, I perturb y by y plus delta y, and I perturb z by z plus delta z. Now, when we calculate the Lyapunov exponent, we basically see how this perturbation or how this separation evolves as a function of time. Okay, so let us first look at the x perturbation, though the other ones will follow as they do. So we have to calculate what ddt of delta x. What is this quantity? So this can be written as, so f of x, fx basically represents the velocity in the x direction. So this is the gradient of velocity in the x direction multiplied by delta x. All right. So the evolution of the perturbation is basically written in terms of this expression. And this basically means that if the velocity in the x direction is increasing, then the perturbation size will increase. So how does that come about? So if you now solve this equation, you get delta x at time t is nothing but delta x at time t0, which is delta x naught into exponential of del fx del x into t. Okay, so this basically means that if this quantity is positive, then the perturbation delta x grows in time. On the other hand, if del fx del x is negative, then the perturbation decays with time. Similarly, you can also find same expressions for del y of t, which will be del y naught exponential of del fy del y into t and del z as a function of time, which is del z naught exponential del fz z as a function of time. Okay, so this tells me how the perturbations del x, del y, and del z grow along the three axes or the three different directions. And if I look at the perturbation vector, which is del x at any instant of time, it is nothing but the sum of these perturbations as a function in the x direction plus del y in the y direction plus del z in the z direction. Okay, so then the magnitude of the perturbation is basically given by the sum of this, or the norm of the perturbation is basically given by the sum of the squares of these things. Okay, now coming back to the volume expansion. So a volume in phase space, if I consider an infinitesimal volume like this, then let's suppose these axes are basically del x naught, del y naught, and suppose this I call del z naught. Okay, suppose now this thing evolves to a certain different kind of a volume after a time t. Okay, so then what will be the volume of the object at time t? Then the volume of the object at time t is basically given by del x, del y, del z, all of them evaluated at that time t. And this is nothing but del x0, del y0, del z0 into exponential of del fx del x plus del fy, right, del fz del z. So this is what we had seen before. Now, basically, these quantities, the gradients, these tell us the growth of the perturbation which was taken in the different directions. Okay, so essentially they represent our Lyapunov exponents. So this is say lambda x, this is lambda y, and this is lambda z. So, or it can be taken as lambda 1, lambda 2, and lambda 3. So lambda 1, so if I take the largest expanding direction, if you look at this volume over here, so this volume seems to be expanding in this direction. If I now rotate my axis and take this as the largest expanding direction as lambda 1, then the other two directions which are orthogonal to this direction will be the other two axes corresponding to the Lyapunov exponents lambda 2 and lambda 3. So if the phase space is n-dimensional, then there will be n orthogonal axes, and considering the direction of the maximum expansion as lambda 1, the other exponents will follow from that. So essentially what we get is that P at time t is equal to P at t0 into exponential of summation over the Lagrange of exponents into time t. Okay, so this is what the volume expansion or what rate of change of volume looks like. So you see that the rate of change of volume, it always depends upon the sum of the Lyapunov exponents. And since I considered the maximum expanding direction to be lambda 1, what we usually do is that we arrange the exponents in decreasing order. We call lambda 1, that means the first Lyapunov exponent, as the maximal Lyapunov exponents, and all the subsequent Lyapunov exponents like lambda 2, lambda 3, all the way up to lambda n, these are basically the eigenvalues in the other Lyapunov exponents in the direction in basically in the orthogonal directions. And these orthogonal directions are basically or the ones which are orthogonal to with one of the axes lying along lambda 1. Okay, so this entire set of exponents lambda I, where I goes from 1 to n, this is known as the Lyapunov spectrum. So this is what we call a Lyapunov spectrum. Okay, so what is the next thing? Okay, so we saw that the volume contraction. So the contraction of the volume depends upon this summation n equal to 1 to n lambda n. So if this is negative, this implies volume contraction in the phase space. And if this is greater than 0, it means volume expansion in phase space. So what do these two things mean in principle? So if there is volume expansion, then any infinitesimal volume size will go on increasing with time, and it will finally go to infinity. In other words, the trajectory starting from any point in phase space would finally end up at infinity as time tends to infinity. So that is what is meant by volume expansion, and that happens if the sum of the exponents are greater than 0. On the other hand, if the sum of the exponents are less than 0, it is the more interesting case, because there can be two. One thing for sure that happens is that there is volume contraction in phase space. So the trajectories never go off to infinity. They always have to stay within some bounded volume in phase space. Even if the trajectories they start from infinity, they ultimately come to a bounded region in phase space, and finally the volume of the ball of initial condition, it goes to 0. That means it can either go to a point, or the initial conditions can ultimately approach a line, or it can approach an area or some other dimensional object. So the volume contraction thing, the sum going to negative things, has two implications. One is that the system only has stable fixed points or attractors. That is for sure. The attractors can either be stable fixed points or the regular attractors which we see. And the other consequence is that there can be strange attractors, like we saw for the Lorentz equation. And the strange attractor implies chaos. So what is the difference between all the attractors being regular and strange, I mean the attractor being regular and strange. So the difference comes from the maximal Lyapunov exponent, which is lambda 1. So you saw that all the Lyapunov exponents are usually in decreasing order. So lambda 1 is greater than lambda 2, greater than lambda 3, and so on. This is greater than lambda n. Okay, so if lambda 1 is less than 0, that means that all the exponents, all the LEs are negative, right? So when this happens, basically it implies that if you look at the individual perturbations, then del x, del y, del z, for example, over here, then this basically means that each and every perturbation will ultimately decay to 0. That means that no matter how far away the initial conditions are from each other, they will always approach each other and finally follow a common trajectory. And that common trajectory can either be a fixed point or a stable limit cycle. So lambda 1 less than 0 basically implies that there can be no chaos in the system. On the other hand, if lambda 1 is greater than 0, then regardless of the values of the other exponents, whether they are less or greater than 0, it means that two nearby initial conditions will always have a growing direction. So there is always a growth in the the initial separations, and what happens is that the separation vector of the initial conditions, it tries to align along the direction of the growth with time, and then it will keep growing with time. So that is what lambda 1 greater than 0 implies. And this basically means that the system is chaotic. That means there is sensitive dependence on initial conditions. So no matter how close to initial conditions are, because lambda 1 is greater than 0, that infinitesimal perturbation will always grow with time. Okay, so this is what we mean by Lyapunov exponents, and this is what we use to quantify the sensitive dependence on initial conditions, or the amount of chaos, or quantify chaos in a system. So how do we calculate the exponents lambda 1 and lambda 2? If you see, look at these equations over here of delta x, delta y, delta z. This approximation we make over here, we make the when we integrate this equation to get this equation, then we assume that delta fx del x, this is independent of time, or this is constant with respect to time. Now this assumption is possible only if we track the trajectories for a short period of time. Right. If you track the trajectories for longer, then this quantity will no longer be a constant of as a function of time. So then how do we calculate the different Lyapunov exponents when we try to solve it on a computer? So there is a method for this, and this method depends upon the Gram-Schmidt orthonormalization procedure. So the things that we do is that we consider two initial conditions. I mean, we consider an initial perturbation vector like this. Okay, the perturbation vector can be in any of the three directions. Basically, we consider an uh, yeah, Hold on. So the main thing that we assume is that we first try to linearize the system because we only solve for short time intervals. Okay. So linearization, when we do, so we basically have to first find the Jacobian matrix. All right. So Jacobian matrix is given when I look at the three-dimensional system, for example. So this is the Jacobian matrix. Okay. And we have the system as x dot equal to f of x. All right. So then if you consider a perturbation vector, this is nothing but the Jacobian matrix times the perturbation vector. So this basically is an equation which tells about the linearized evolution of the perturbation. All right. So then if you have to then basically if we try to solve this equation, then we get we have to solve this particular equation numerically. So this basically means that delta x at sometime t0 plus delta t is equal to delta x at time t0 plus j dot delta x time t0. So this means that the perturbation after an infinitesimal time interval is nothing but the perturbation, the identity matrix plus the Jacobian at time t0 dot product with the perturbation vector at time t0. So this is the equation that we have to solve numerically. And to obtain the Jacobian, we need to solve the original flow equation, which will give us x, y, and z at time t. And using x, y, and z at time t, we can evaluate the Jacobian matrix. All right. So if you now evolve this perturbation equation, you basically get delta x, right? The perturbation. So as you can see, initially we can choose a random perturbation vector, which is basically delta x naught, which has components, rather I should write this as capital X to avoid confusion, delta x0, delta y0, and delta z0. So these are the three components of the perturbation vector, and initially we choose them to be orthonormal or orthogonal to each other. Okay, now what you do is that you evolve it for a single time step, and then you calculate, then you evolve for one step, then you obtain the new vector, which is delta x at time t plus delta t. Okay, so the components of this vector are basically delta x, delta y, and delta z, all of them evaluated at time t plus delta t. Okay, now you see that delta x, delta y, and delta z after this evolution, they won't be orthogonal to each other. Essentially, what happens is that this vector delta x, it points in the direction of the largest expansion. Okay, so it at long times it points in the direction of maximum expansion. Okay, and that direction corresponds to nothing but lambda 1. So what we do is that if you keep on evolving this equation at every instant of time, then what will happen after a certain number of iterations is that the direction of maximum expansion will keep on going as it is, but the other directions which don't expand fast or the ones which contract, they will become so small that it will give rise to numerical errors. So it will go down below the scale of the smallest numerical value that can be resolved by a computer, and that can give rise to errors in the long time evolution. So after evolving for one step, we do the orthonormalization, which is also known as Gram-Schmidt orthonormalization. So how does this Gram-Schmidt procedure work? So basically, if you have a ball of initial conditions, okay, so if you have these components delta x, delta y, and delta z, and the vectors pointing in each of the three directions are not orthonormal to each other, sorry, there was a mistake over here. I think I should repeat the explanation from this point onwards. So what we do is that we start off with not a single initial condition, but a single perturbation vector, but a ball of initial conditions whose three vectors, basically n vectors can span the whole n-dimensional volume. Here we consider a three-dimensional system, so we consider three vectors which span the whole volume. So we take the three vectors in three orthogonal directions. So we initially take three orthogonal vectors which are del by 1 and sorry del x 0, del y 0 and del z 0. Okay, so then we basically have this 3 by 3 matrix. Have a 3 by 3 matrix over here. The three vectors in the three orthonormal directions. Okay, after this, what you do is that you evolve each of these three vectors using this matrix equation of the Jacobian. So if you call this matrix, say capital, or you can call this matrix, for instance, say V naught. So basically, V naught represents a volume in phase space. So then you have to solve the evolution equation of this matrix V. So this is nothing but the matrix A dot with the matrix V at time t. So this basically, if you try to solve this numerically, this becomes the matrix E at time 0 plus delta t is nothing but matrix V0, sorry, V at time um, basically becomes the identity matrix plus the J matrix into delta t, product with the matrix V at time t0. Okay, so this is what the evolution equation looks like. So basically, the evolution of the volume of initial conditions, that means the initial evolution of the initial perturbation volume is basically the same as the evolution equation for this vector. So this basically follows if you have all three vectors over here, and this looks like this particular equation. Okay, so this is what governs the evolution of the volume of initial conditions. So you see that after you start off with these equations, then basically the volume V that you get from here, it is given by the three perturbation vectors delta x, delta y, and delta z. So after uh, time delta t, these vectors which form this matrix V, they may not be orthogonal to each other. So what happens is that, as I mentioned, they all the one which is along the was one of them tries to expand while the other vector. So basically, what happens is that you start off with an initial condition which had three orthonormal vectors, and after time t, because each and every vector tries to align along the maximal expanding directions, you will have all three vectors aligning like this. Okay, so then that will give errors in the computation. Okay, because of the three Lyapunov exponents. In other words, you will only get the largest Lyapunov exponent, but you won't be able to calculate the rest of the exponents in the spectrum. So in order to get the full Lyapunov spectrum, what we do is that we do a orthonormalization over here. So what we do is that basically we do uh, Gram Schmidt normalization. And how does this work? So this basically means that um, suppose you have a matrix which comprises of the vectors delta x, delta y, and delta z. You take the first direction, or you can say for simplicity there R1, R2, and R3. So R1 basically corresponds to the largest expanding direction. So what we do is that we evaluate the sizes of the perturbation vectors, and we see which one is the largest of delta x, delta y, and delta z. So the largest one will correspond to the largest Lyapunov exponent, which is lambda 1. So suppose this one corresponds to lambda 1, this one corresponds to lambda 2, this one corresponds to lambda 3, and the order is like this. So what we do is that we keep R1 fixed. So R1 is fixed, and then we try to orthogonalize the second one with respect to the first one. So what we do is that suppose the angle between R1 and R2 is theta. That basically implies that R1 dot R2 is equal to R1 R2 cos theta, or the projection of R2 in the direction of R1 is basically given by R2 cos theta. So then we need to take a projection in the other direction, right? So this is R1, this is R2, and this is theta. Then what will this be? This will basically be R2 sine theta. So we take the projection of R2 in this direction, and then the new vector R2 basically becomes R2 sine theta into the unit vector, new unit vector R2 cap, where R2 cap is the unit vector in this direction, which is orthonormal to R1. And similarly for R3, we orthonormalize that vector with respect to both R1 and R2. And then we get the new vectors R1, R2, and R3. So we call the new vectors, say, R1 new divided by n, R2 n, and R3 n. So these are the new vectors which we get after orthonormalization. And this one is nothing but the same as the earlier one, R1. And the magnitudes of these vectors, it depends upon the angle theta. So you see that when theta becomes very small, that means when R2 and R3 become very much aligned with R1, then the magnitudes of these vectors become very small, and that can give rise to numerical errors. So what we do is that we orthonormalize them, and after orthonormalization, we get the new vectors, which is R2O and R3O. So this new set of vectors we finally get at the end of this procedure is basically another ball of initial conditions such that one of the axes, which is defined by basically the three orthogonal axes, such that one axis is along the direction of maximum expansion. So this is basically the Gram-Schmidt auto-elimination procedure. And after we do this, we again go back to this step where we solve the equation for evolution of the perturbation at the next time step. And if you repeat this procedure for uh, up to time t equal to infinity, then each of and or sorry, I one thing which had to mention here was that, and what is the Lyapunov exponent that we evaluate at this step? So we had seen that delta x is the largest among the three perturbed vectors, right? So then we calculate at each step the largest Lyapunov exponents, or in other words, lambda n is basically given by 1 by delta t into log delta x at, for the sake of simplicity, we do this gamma n, right? Issued of vector delta xn at time t0. Okay. And we vary t0 and calculate this at every instant of time. Okay, so instead of t0, we can call it t, and this is then gamma n as a function of t. So this is evaluated at every time step. And finally, we take the limit of the Lyapunov exponent lambda n. This is basically given by the mean value of gamma n as time t goes to infinity. So this is basically given by 1 by k summation over gamma n 1 to, let's say, some capital number m. Okay, where what is the value of m? Where m is nothing but the total time t by delta t. This will also be m. So this gives me my Lyapunov exponent lambda n. So, or to be more precise, lambda n is given by the limit of t going to infinity. M is basically what? So upon evaluating the summation, we get the final expression for the Lyapunov exponent. Okay, so now after 5 minutes, I will show you a code which actually does this calculation of Lyapunov exponent, and then we will see how it can be applied to certain real world applications like turbulent flows. So the system for which I will show the calculation of the Lyapunov exponents is the Lorentz system. So let us recall what the Lorentz equations had looked like. So the Lorentz equations are basically given by um, xy minus dz. Okay, so the first thing that we need to check is the Jacobian matrix of the system. So Jacobian is given by so this is the Jacobian matrix. One interesting thing that you can directly read out from the Jacobian matrix is what is the trace of the Jacobian? Trace is nothing but minus sigma minus 1 minus v. And this was nothing but equal to the rate of volume contraction, which we had seen in the previous class. So the trace of the Jacobian basically gives me this quantity, which gives me the rate of contraction or expansion of an infinitesimal volume. Okay. So once we calculate this Jacobian, we can take we can take the initial perturbation matrix. That means the matrix V at time t0, which is the matrix of perturbation vectors. And we since they are to be orthonormal, so this has to be basically an identity matrix. Okay, whose initial directions can be chosen along any direction. Basically, we can simply take the XYZ orthogonal directions to be the eigendirections. Henceforth, and beyond this, the directions will coincide with the direction of the maximum expansion. So then once we know this, we multiply this with J with V, and then we evolve this equation, and at every step we calculate the quantities gamma n and then sum over them to obtain the eigenvalues lambda n. So now I will stop sharing this screen and share the other screen to demonstrate what this calculation basically looks like. So this one is the code which I had shown yesterday on lab of exponents, and we have done the calculations in this portion over here. So what we do is that we evolve the trajectories for a very long time. As you can see, we have 1 lakh iterations, and we then evolve the perturbation vectors only beyond a certain initial condition. So that what we do is that we we neglect the transients. We first allow the initial, we allow first the phase uh, phase space phase space trajectory to first settle into the attractor. And once it settles into at the attractor, we consider a small ball of initial conditions around that particular phase space trajectory. And that ball, we take it to be an identity matrix multiplied with a very small perturbation vector delta x. But since we again orthonormalize it, so the magnitude does not matter. So, and then we, in this step over here, we basically have the matrix J, which is the sum of the identity matrix and the Jacobian matrix over here, multiplied by delta T, which is given by H. And then what we do is that we multiply this with the matrix W. The matrix W is equivalent to the matrix phi, which we had shown earlier while doing the calculation. So W is the new matrix of perturbations. And after we get the new matrix of perturbation, we perform this Gram-Schmidt orthonormalization. So one useful way of doing this Gram-Schmidt procedure is to do a QR decomposition of the matrix W. So basically, it decomposes the matrix W into a matrix Q, which is a matrix of orthogonal eigenvectors, matrix of orthogonal vectors, and an upper triangular matrix R, whose diagonal entries basically are the eigenvalues corresponding to the vectors of the matrix Q. Okay, and these eigenvalues of the matrix R, which are the diagonal elements of R, they basically correspond to the uh, three Lyapunov exponents, and they are arranged in decreasing order by default. So the first diagonal entry of R is the largest one, then the smaller one is the next one, and finally the smallest one is the third one for the Lorentz system. Okay, and these uh, uh, give me the Lyapunov exponents, which are stored in this array known as lam. And this equation is evolved at every step. So every step we get the we calculate these values which get stored into the array lam, and these values which get stored in this array over here, these basically correspond to the gamma n which we had shown previously. So we calculate all the gamma n's, and finally what we do is that we sum over all the gamma n's and divide it by the total length of the time series to obtain the final Lyapunov of exponents. All right, so we run the code. Yeah, as you can see, let us see what the Lyapunov exponents look like. So you see over here for the Lorentz system, the largest Lyapunov exponent corresponds to somewhere close to 1, and most importantly it is positive. So since it is positive, this underlines that it is a chaotic system, and the second largest one is close to 0, and the last one is negative. So if you calculate the sum of all the Lyapunov exponents, then you see that the sum comes to around this value, which is minus 13.7. Okay, now we had said before that the sum of the Lyapunov exponent basically gives us the rate of expansion or contraction of the volume. So here the rate of volume contraction, it turned out to be minus sigma plus 1 plus b. So here we have this values of sigma as 10 and b is beta. So if we try to calculate this thing, so minus sigma plus 1 plus beta, this quantity turns out to be 13.667, which is very close to this quantity. So both of them are roughly equal to minus 30.7. So this basically shows that the sum of Lyapunov exponents is nothing but the rate of volume contraction of an infinitesimal volume in phase space. Okay, so that was a demonstration of the Lyapunov exponents for the Lorentz system. For any chaotic system, this procedure of calculation of Lyapunov exponent holds good. So basically, if you know the dynamical equations, then you have to find out the Jacobian matrix. And then from the Jacobian matrix, you solve the linearized equation for the perturbation at the flow points at every time instance. And once you get the perturb vector after a given iteration, you orthonormalize that vector, and then you again repeat this procedure of finding the Jacobian and evaluating the perturbation vector. And in this way, you can calculate all the Lyapunov exponents of the system. Okay, so I stop sharing the screen now. So now the most important application, one not most important, but one of the important applications of Lyapunov exponents comes in the context of turbulent flows. So in turbulent flows, you can imagine that there are suppose the turbulent flow, it carries with it a number of particles, and the particles can follow different trajectories. And then you can ask the question that suppose if two particles are very close to each other, then over short time scales, they separate out exponentially like the perturbation vectors did in our case for this dynamical system. Okay, so then you can ask what are the Lyapunov exponents of those particles. So this brings us to the concept of what are known as finite time Lyapunov exponents. So finite time Lyapunov exponents is actually a very simple concept if we know this calculation of the Lyapunov exponents. So what those things are? So basically, we had these vectors, these numbers. Okay, where were the numbers? Gamma n. Yes. So we basically had quantities calculated these gamma n, which were basically obtained from the increments over small time instances, and then we had summed over them to obtain lambda n. So instead of summing up to time t equal to infinity, what finite time Lyapunov exponents, we can call them as lambda x. So what happens is that lambda n considers the summation over gamma over finite time intervals t. Okay, so k equal to 1 to t by delta t summation over gamma n k. So here for finite time Lyapunov exponents, t is finite. So basically what it does is that it tells us in a finite time interval, how does this perturbation grow? And you will see in turbulent flows, this finite time interval matters because across different time scales, the perturbation can grow in different manners. So these FTLEs are very important to find out which places in a flow are coherent and which places are not. What I mean is that suppose you have many particles like this, they are evolving in random directions. Okay, now suppose there was a coherent object in a flow like this. And a coherent object is such that every particle on it, it evolves coherently across over a certain time scale t, or say for suppose capital T. So if they did evolve coherently for capital T, then you see that for all the time scales small t, which are less than capital T, gamma n will be negative or small quantities, right? So if they're negative or small, then even the lambdas will be small quantities, right? Because they evolve coherently over such time scales. So if you plot a map of lambda as a function of the initial position of each particle, so lambda is evaluated for each particle in the flow, and if you plot a function lambda as a function of the initial position of the particles, then you will get a graph which looks like this. So suppose I have a two-dimensional flow, this is x and this is y. Okay, you will see structures like that in this graph. Okay, and in these structures, the value of lambda, say, is small for a given time. For a given time t, the value of lambda within these structures is very small. So this basically tells us that the particles within these structures move coherently. That means any perturbation around that particle, it does not grow to very large values. And so this basically gives me structures, the coherent structures in the flow, which are called the Lagrangian coherent structures. And evaluation of coherent structures in turbulent flows is very important because it gives us useful insights into the underlying dynamics of the flow. For example, it is usually conjectured, but it is very difficult to prove mathematically that the entire flow is basically a sum of all these coherent structures. Okay, so this is a very intuitive thing, and it is very difficult to prove mathematically. It has not been done till now. But yeah, so if you find such coherent structures in the flow, you would see that there is actually a bit of order in this whole chaotic behavior. So this basically gives us insights into how order can arise in in spite of the flow being chaotic and so on and so forth. Okay, so the next important thing about such strange attractors and chaotic systems is the second part of the discussion, which we had mentioned, and that is the concept of fractals. So fractals, as we had said earlier, the description had seemed very abstract, but they are basically fractional dimensional objects. So their dimension is not an integer. For example, if you have a rod, it's a one-dimensional structure, a sheet of paper is two-dimensional, the world around us is three-dimensional. But fractals are basically objects whose dimensions are none of these. Their dimensions are non-integer values. Okay, so that is what makes these things very interesting. And when one talks about non-integer dimensions, then it might seem at first instance that these structures do not exist in the real world and they are abstract objects, but that is not the case. Fractals are more common in the real world than one can even think of. For example, if you look at the structure of coastlines of countries or the structure of mountain ridges and structures of valleys and so on and so forth, even the small scale structures which can form in turbulent flows and so on, all of these things have a fractal structures. Okay, so what defines a fractal? So a key thing in the definition of in the characteristic of a fractal is its self-similarity. So what do we mean when we say self-similarity? It basically means that if you take a fractal object and you keep zooming into that fractal object, you will see self-similar structures. Basically, if you zoom into that object, you will basically see a replica of the larger object. And you zoom in further, you will keep on seeing these replicas repeating one after the other. And despite zooming in, you will see that the zoomed in object, it looks the same as the larger object. So self-similarity implies there is a scale-free nature. So fractal objects do not have a fixed scale. So no matter which scale you look at, they always look the same. So in other words, we call them scale-free objects. So what do they look like? So for example, by the way, fractals are not always exactly scale-free. The scale-free property is, cells fractals, exact cell similarity is rarely seen in the real world. Cell similarity is always broken at some scale or the other, or there might be different kinds of cell similarity convoluted into one object. Okay, so that we'll come to later. But what do we see when we say cell similar objects? So let us start off by drawing such an object, which is known as a Cantor set. So a Cantor set is a simplest one-dimensional fractal one can think of, but mathematically it is a very interesting object. So suppose you have a line like this from 0 to 1. What you do is that in the next step, you remove the middle third of the line. So remove the line from this portion to this portion, and you get objects like this. You see? So if the length of this segment was L, this is L by 3, and this is L by 3. So this one was iteration 1, you call this iteration 2. Similarly, in iteration 3, since fractals are self-similar, one way of constructing fractals is to repeat the same pattern of operation again and again. So again, I repeat this operation on this line segment. So again, I remove the middle thirds. I get something which looks like this. Okay. Here also, I remove the middle thirds. I get something which looks like this. And each segment here has length what? L by 3 into 1 by 3, which is L by 9, right? Again, I repeat the same procedure. I divide this like this. So you see what I'm doing. So if you zoom in like this, if you zoom into these objects, they basically look the same. So finally, you would get a very fine structure which looks the same at all scales. So if you zoom into this particular line between these iterations, this looks the same as the first one. And similarly, this one looks the same as this one, and this one if you zoom in more and more. So this is what is known as a Cantor set. Similarly, you can also have other kinds of fractals. Okay. By the way, if you try to calculate the dimension of this object, this lies somewhere between a point and a line as n goes to infinity. So this will be more clear from this example. So this is known as a Hirsch curve. So what we have here is something which initially you have a line like this. Then what you do is that you add a, you take the middle third of the line. So this L by 3, L by 3, L by 3. You remove the middle third of the line and prop up two lines which look like a triangle. Okay. So the length of each of these segments is L by 3, L by 3, L by 3, and L by 3. Okay. Now on each of these segments, you repeat this procedure of removing the middle third and putting a triangle of 1/3 the length of that segment in its place. So then it will look something like this. So the initially the length of the line was what? Line was L. But now the length of this new curve, which is no longer a line, its length is what? L by 3 into 4, right? Its length is 4L by 3. Similarly, if you look at this line over here, the length of each of these segments is basically L by 9. And how many segments are there? 1, 2, 3, 4. 4 here, 4 here, 4 here, 4 here, there. Okay. So the length of this new curve over here is what? 60 by 9 into L. So you see there is a certain pattern in which the length of the curve is increasing. So here the pattern was basically at every step you were multiplying the length by 1/3 and the length was decreasing. Here at every step what happens is that you multiply the length by 4 by 3. Okay. Similarly, if you go to the next iteration, things start looking even more beautiful. So something like that. Okay. So you see what's happening here. The length of the curve is 64 by 27L, or in other words, this is nothing but 4 by 3 cube L. So after n iterations, what happens is that the length of the curve will become 4 by 3 to the power n into L. And then the final object that you get, I mean, you can see it from here itself that this thing, it is now no longer a line which we had earlier. Neither is this a surface because it does not close in upon itself. In fact, it looks somewhere between a line and a surface. So as we will show that the dimension of this object lies between 2 and 3. Similarly, there are other kinds of fractals. So the first one was formed in one dimension from a line and in all those areas and so on. So this line was broken up into dots like that, and you have this line which was built into a sort of thing which looks close to a surface but not a surface. Similarly, you can have another type of fractal called the Sierpinski carpet. Okay, so basically the repeating motif over here is that you have this two-dimensional object like this. Okay, and what you do is that, so we had shown that you can build up something from one dimensional to something which is higher than one dimensional using this idea. The Sierpinski carpet, what it does is that you have the triangle, then you remove this middle portion of the triangle. Okay, then you have these three triangles. Again, you repeat the same procedure. You remove this part from here, you remove this part from here, and you remove this part from here. Okay, then again, you again have these small triangles. You remove the middle parts like that. So you see what is happening, and again you repeat the same procedure for all these small triangles. So then what was initially a two-dimensional object, but since you now start removing portion of it, its dimensionality goes down, and then it becomes somewhere between a 1D and 2D object. So these things we followed a particular rule of exact cell similarity. But basically, it meant that we were repeating the exact operation across different iterations. So you can also have something where we do not repeat the exact operation, but then you also get a fractal. So what I mean is something like this, similar to the triangle example which you saw earlier. So suppose you start off with a square. Now you divide it into 9 squares like this, and you pick any one square at random. Say this one, I remove this one. Okay. Now you repeat the procedure again for all of these things. So basically, so you have we divided what these squares which are marked over here into smaller squares like that. And in each of these large squares, we have these 9 small squares. We pick a square at random, this one at random, we remove this one, we remove that one. Here we can remove this one, that one. Then for this one, we can remove this. For this one, we remove the middle one, and this one, this one. So you see, you can remove objects like this, and then you can go to finer and finer scales. So initially we had started off with removing this particular square, but for the other squares at the next step, we remove the squares at random. And if you keep on removing such objects, basically, if you just tweak the operation and put in some randomness into the operation, then you would see that you won't get exactly cell-similar patterns, but something which is close to cell-similar. And such randomness can in fact give rise to intermediate patterns as well. And this is very important when it comes to real world systems, because real world systems are never exactly self-similar, yet they have a fractal dimension, yet we call them fractals. So that they are formed because the physical processes which form them are not exactly self-similar. They have some randomness in them, and this inherent randomness can break self-similarity, can give rise to new kind of self-similarity, which are basically convoluted into one particular object, which are basically convoluted into one. So how can we quantify such self-similar behaviors? How can we quantify fractal dimensions using fractals? And how such Self-similarity or broken self-similarity is important in physical objects like turbulent flows and so on and so forth. All these things we will learn in the upcoming lectures. Okay, so that's it for today.